Hello, welcome back to Quantum Computation Explained series of videos. I'm Kadresan. In this video, we will learn about phase kickback, what it is, how it is getting implemented, what is its use, and things like that. Okay, so what it is, it's actually a strange phenomenon, something similar to superposition and entanglement in quantum system. But it's very useful, and that's why it is utilized in many algorithms like DJ, source, Grovers, and many more. It comes into existence when we handle multiple qubits with controlled gates. So typically what happens in a controlled gate? So we have two qubits, one is in control, the other one is in target. Okay. So this can be NOT or any other gate. So whenever we want to do, when this state of this qubit is 1, so you will do some action on this qubit. But phase kickback does something reverse, okay? Instead of doing it on here, it kicks back, it gives back that action to the control qubit. So that's the essence of phase kickback. We'll know more about this with some example in subsequent slides. Alright, is there any condition under which phase kickback works? Yes. The condition is the target qubit needs to be an eigenvector of the operator U or whatever unitary matrix we are having here. Okay. And before we jump on to phase kickback, let's try to understand what is phase. For some of you, okay, it may be a refreshing thought. So there are two types of phases. One is global phase and relative phase. So what is phase? Suppose we want to represent state of a qubit in block sphere. Whatever we project the state onto this horizontal or equatorial plane, the angle what it makes with the x-axis is pi, which we call it as phase. So mathematically we try to express it like this: e to the power of I pi into the state alpha ket 0 plus beta ket 1. And when you want, and generally it does not, I mean not generally, always, it does not affect the probability of measurement in any basis. Why is it so? So whenever we want to take the probability, we take the amplitude square, right? So at that time we will be multiplying e power I5 with e power minus I5, which will result in 1. So the amplitude or the probability depends only on alpha and beta for these two states. That's why we don't consider, we neglect it, or in fact we don't really worry about study or talk about global phase. So but relative phase is an important one. So what is it? So maybe we can represent like this: e to the power of I pi 1 for ket 0 and e to the power of I pi 2 for ket 1. And if you want, we can take e to the power of I pi 1 outside. So that makes this statement, which you can see here, it is of the form alpha ket 0 plus beta into e to the power of I some constant. Okay. So this is how it looks like. So this value, which corresponds to the relative phase actually. You can also represent it here, but this is the normal practice to put it with respect to the ket 1. Okay. It affects the probability of measurement. Is it always? No. It depends on the measurement basis what we are working on. For example, let's take two states or two qubits in two different states. One is in plus state, another one is in I state. So in the block sphere, so one is here extended the x-axis where it meets the circle, and the other one is somewhere here. Okay. If our measurement basis is z, that is 0 and 1, then there is no difference. Both will result in both 0 and 1 will get in with 0.5 probability. But if our measurement is x, then what happens? This will go, will result in probability of 1 in plus, whereas this will have both plus and minus with equal probability of 0.5 each. So you can see that the probability of measurement gets affected depending on the measurement basis what we need to work on. So how does it work actually? It's like we know that when we have two waves with some phase difference, and if they interfere constructively, the amplitude goes up, and destructively the amplitude comes down. So this also works something similar to that. So if you are able to effectively use, you will find a lot of applications for this one, phase kickback. Okay. And yeah, you can learn more about phase like what is given here. Of course, I given these references at the end of this video, but for a programmer I think this should be sufficient. So the takeaway is we are not interested in global phase. We will be interested in relative phase, and which is generally expressed like this. Okay. All right, now we'll learn about phase kickback. So before that, I think this you are familiar, I hope. So whenever an operator works on a state psi, the resultant will be e to the power of 2 pi I pi state psi. So, but there's a condition here that this should be the eigenvector of this operator, and this is nothing but eigenvalue, the corresponding eigenvalue of that operator. Okay, this equation, we'll be using it subsequently. Let's start with 2 qubits. Okay, one qubit is in state 0 and another qubit is in some arbitrary state psi. Okay, and we are going to add a Hadamard gate to the first qubit which is in state 0. So what you will get? Hadamard gate will take this qubit to superposition state, the equal superposition of 0 and 1, which is also called plus state. So we can represent like this. This is the first gate and this is the first qubit and second qubit. And this also can be expressed like this, taking tensor product. Okay. All right. So here we have plus and psi. Now we are going to apply controlled U gate. So the U gate will be applied to this state, the state of second qubit, only when the state of qubit is in 1. But now we are in superposition. That means whenever 0 is there, there is no effect. It will come as it is. But when there is 1, this gate will get added, or this operation will be done. And we know that this operation will result in like this because of this equation what we seen here. Now if I take psi, ket psi out, you will get ket 0 plus e to the power of 2 pi ket 1. That is nothing but the state of this, and psi is as it is without getting disturbed at this point. So whatever we intend to do, it's kicked back to the control qubit and not the target qubit. So this is what is called phase kickback. I hope it's clear. Now let us see maybe some more examples and see how it is used in other algorithms. Okay, so there's some interesting steps. Whenever we apply C0 gate to plus, nothing happens. But when the target qubit is having some phase, it adds a phase to the control qubit. So the first one is control and the second is target. Yeah. All right, you will get minus. But if it is minus plus, nothing happens, it comes as it is. But if it is minus minus, then again there is change in the phase here for the control qubit, and target qubit remains as it is, then we'll get plus minus. Okay, so let's see some mathematics for plus minus. Sorry. So we'll start with 0, 0. So this will become 1, and this will become plus, and this will become minus. Okay, plus minus. And to which, when we add a control gate, what happens? Let's see. This both will become minus minus. Let us see how it happens. Okay, so 0 and 1 before we apply Hadamard gate. Okay, so we have 3 gates here, 2 Hadamard gates and 1 CNOT gate. So when we apply 2 Hadamard gates to 2 different qubits, the tensor product will result in H, H, H minus H, right? Because H is nothing but 1, 1, 1 minus. So this is the unitary matrix corresponding to this Hadamard gate. So we are having one H here, but these two H elements have got disturbed because of the CNOT. I mean, you can verify this whether this is done correctly or not, but yeah, we know that it is done correctly. Okay. So now 0, 1 can be represented as 0, 1, 0, 0. We know that. So when you do a simple matrix multiplication, the result is 1 minus 1 minus 1, 1. And we know that this value corresponds to the amplitude for this state 0, 0. This is for 0, 1, 1, 0 and 1, 1. Correct? So that is what is written here. You have plus 1, minus 1, minus 1, plus 1. And luckily, these two qubits are not entangled. Okay? If this H was not there, it would have got entangled. But luckily, since these two qubits have not got entangled, we can represent them in 2 different qubits with a tensor product symbol. That is done by taking ket0 minus ket1 out from this expression. You will end up with another ket0 minus ket1. So both represent minus minus state. Okay, so this is what we have seen here. Okay, now let's see some application of phase kickback. All right. So the first one is, you can see it in Grover's algorithm, wherein you know that we will be having superposition of all possible combinations or all possible states using the given number of qubits. Suppose we have n qubits, it's possible to have 2 to the power of n possible states here, correct? So out of which generally we'll be interested in one or few states. Okay, so that is done with the help of phase kickback. So in order to do that, we'll start having another qubit in minus state, and this phase will be kicked back to the one what we are interested in, okay, with the help of an oracle. So for that particular state which we are interested, a negative phase will be added. For all others, they remain in their respective states, okay. And subsequently, you know that what we'll do, that particular state will increase the amplitude of measurement by having a diffuser operator, and we'll try to repeat this process many number of times till we get a satisfactory probability value, okay. So it's very nicely used in Grover's algorithm. And in quantum phase estimation, what is our interest is, we need to get what is the phase associated with a given operator u. So in order to do that, what we'll do, we have to start with a set of, with eigenvector of u. So that is what is done in this register. We'll try to represent the eigen vector with the required number of qubits. and these qubits are output qubits, which are actually by which we are going to get the answer. So we'll start with the state 0, then we apply Hadamard gate. One question will come to our mind: how many qubits I should have? So that depends on what is the accuracy what we are looking for, and what is the probability value which we are looking for. Okay, accordingly we'll select the number of qubits, say we'll call it as T. Then what we'll have to do, we have to apply controlled U gate. Okay, first you apply 1 here one time, then subsequently you apply U square times, like that you keep adding, and for the last qubit you apply 2 to the power of T minus 1 times. So what is T? The number of qubits what we have here. So now what happens, the phase associated with this operator, they get embedded into these qubits. Okay, I'll not go into the detail, possibly I'll give another video with explaining these terms. So once we have the values in terms of angles, we need to read out in terms of binary values, correct? So we will try to do quantum Fourier transform, the inverse of it, right? Because we are going to convert angle to numbers, so for which we need inverse Q of t. Okay, and this is used very much in source algorithm, and source algorithm is used for prime factorization. Okay, I hope you have got some idea about phase kickback. Possibly we'll have 1 or 2 sample code running. Okay, so let me take you to IBM QuizKit site. So I already have the code here, and this is given by IBM QuizKit, except that I removed some statements which I felt irrelevant. Okay, so they've imported all the necessary functions from QuizKit library. Then the example what we see here, the code is for applying C0 to plus minus state and get minus minus. So we are having with this we'll have plus in the first qubit and minus in the second qubit. So you can see this is plus and this is minus. Now we are going to add a control, the NOT gate. So with 0, the first qubit as the control and the second one as the target. So what we want to manipulate here, but because of phase kickback, so the state of the first qubit is changed to minus from plus. So we are getting minus minus, like what we have seen in the slide a few minutes back. Okay, I'll take another one in which we try to apply a controlled phase gate. So this phase rotation with respect to z-axis. So we want to give a rotation of pi by 4. So for which again we have 2 qubits. One is in plus state, other one is in 1 state. So when we do this, interestingly you will see here. So this is in 1 state, and this pi by 4, which this was originally in 0 state, now it has got a phase added to that. That's pi by 4, you can see here. Right. Another interesting point here to be noted is whether you use this one as control or this one as control, the effect is same, and that is because this qubit is lying in the state 1, which is right on the z-axis, right? So any phase adding doesn't make any difference. So whatever you add, it gets into the first qubit, which is in superposition. Okay, so I was wondering, well, suppose if I take this qubit also to superposition, what will happen? So that's what I did here. So I took this also to superposition by adding a Hadamard gate and applying again controlled phase gate. Okay, so now something interesting happened. So I don't have an explanation immediately, like what has happened. So you can see both the qubits have got some displacement in angle. Certainly not pi by 4. if somebody knows more about this, please add in the comment column. And if I get some more information, certainly I'll also add. And in state vector form, these two states of a qubit can be represented like this. Of course, this you can easily get it when you do the matrix multiplication or matrix manipulation for these gates. Okay. Yeah, I think that's all I have for phase kickback. And these are all some of the useful references which I had referred. So, of course, the quiz kit is the ultimate documentation you will have. Phase kickback is nicely explained. In fact, the code given there was used by me. And interesting, there are some nice blogs available on phase kickback. I also found it very, very interesting on the question answer given in this website, Reddit, and Stack Exchange. So I recommend you also to go through that. And lastly, the quantum computation and quantum information, the textbook by Mike Nielsen and Isaax. It also explains phase kickback to some extent. Okay. All right, what next? So I'm sure you will continue to work on quantum computing, but I would request you to suggest something similar which will be useful so that I can come out with videos. Otherwise, I'll start working on videos of QFT and QFP. Though I talked a little bit in one of my previous video on source algorithm, I'll give more details about these two aspects. Okay, thank you for watching. See you soon. Till then, bye bye.